Greetings, everybody. My name is Ryan Michael. I'm one of the kind of original creators of this tool called Kaskada that I'll be talking about a little bit. But I want to start with kind of talking a little bit more about, similar to what Patrick was talking about, where AI is going. And I want to start with looking at sort of where we've been, or where we've kind of seen developments already. So we had these LLMs that were kind of developed over the past 5 or 10 years. And a lot of the things that we're discovering they can do have been surprising. So we kind of trained these models to predict what's going to come next over a large corpus of scraped data. And so we sort of expected that they would build some knowledge of the world, right? They would learn what's going on the internet. And so this first level of kind of emergent behavior from these models, I think, is not too surprising. And there's some really interesting things you can do with this first kind of level, as I see it, of capabilities. We've built all these interesting prompt engineering practices. And what we're doing there is we're basically figuring out how can we make clever inputs to the model that give us outputs that we care about. How can we ask it questions? How can we tell it what kind of role it should be playing, things like that. And there's some really interesting use cases that kind of initially were obvious once ChatGPT came out. But then, as we start to move down here, there's some really more surprising things. I think Patrick mentioned the reasoning, but from my perspective at least, the fact that you can take an LLM and give it a bunch of information, like we saw in the RAG pattern, is sort of surprising that it can then summarize that information, because we weren't explicitly training it to do that. This just kind of happens to be something that comes along with the capabilities of these larger models. And what we've been able to do is develop some really interesting techniques to make use of that, right? This is where kind of RAG that we looked at comes in, where we can pull back a bunch of information that's relevant to the problem you've asked it to solve, hand it to it, and instead of it just relying on information that it already has trained on, it can summarize that information or make inferences from that information. Also, few-shot learning, a similar example, where you're gonna give it a couple examples of how you want it to reply. So there's sort of techniques we've developed to take advantage of interpretation and summarization. But what I want to talk about today is this last level, which to me is the most surprising. The fact that these models can actually reason about how to accomplish an outcome and help you plan for them. So you can say, I'd like to, as Patrick mentioned, get from here to some other place. Tell me the sequence of steps that I need to go through, and then it can actually drive those steps. And so what I want to kind of argue today is that there's a new set of techniques that we need to develop to really take advantage of these emergent capabilities. And they're all around what I'm going to call real-time proactive AI. And they're based on the fact that there's a difference in the structure of this problem than there is in these other cases. And the difference is that we are enabling these models to take actions on our behalf. We're not just asking it a question. We're saying, here's something that I would like you to do for me, and I would like you to recognize when there's an opportunity to do this thing. I think there's a lot of really interesting applications that sort of fit into this mold, some more than others. But these are some of the things that I've had conversations with people about actively being developed right now. So I'm going to just kind of share some of these as an example of like where I think this is going and where there's interesting work being done already. Sales prospecting, right? Automating some of the tasks that are repetitive. Prioritizing and summarizing all of your email, right? Could we have an LLM that just reads all of your email, watches all of your Slack conversations, and either responds for you, prioritizes and summarizes, gives you a digest, but basically taking some of the drudge work out of monitoring all of the data you need to be monitoring. Scheduling, rescheduling, having an app that could go gather customer feedback proactively, summarize that and do some sort of product management type work. And then there's a lot of opportunities I've talked with people about, like inventory management. So when do I need to order more toilet paper for my store and whatnot? So what all of these have in common is that we've enabled the model to take action, whether it's going and talking to customers, reading email and notifying you when something's happening. Whatever it is, what we're doing is we're saying, here's an outcome that I would like you to optimize for, and here's some actions you can take. And I want you to do this autonomously without me having to tell you at every step what to do exactly. All of these applications require a different structure of the problem than a QA bot. And this is sort of where I want to talk through the process that I think is necessary for this style of application. It's more of a cycle. The first thing we need to be doing is we need to be watching what's happening in the world. Now, this is different than a QA bot because we're actively absorbing information about what's happening in real time. This is a different style of interface. We're talking about like WebSockets here rather than HTTP. So this is our first step, is we need to be able to be observing what's happening in the world to recognize opportunity. And that's where the second piece is, triggering. So we need to be able to say, okay, I see that I can do something now. There's an opportunity for me to notify you because there's a conversation going on that you might care about, or go order some more toilet paper. And so being able to recognize when to take action is really important, especially given, as Patrick mentioned, the cost of these LLMs. You don't want to just observe everything happening in the world and shove it all through an LLM because it will be insanely expensive. And so being able to have some business intelligence that you provide to say these are the cases in which we want to actually use the LLM is extremely important. From there, we need to take actions. I think that's fairly self-explanatory. We need to make API calls or do various things. I'm not going to get too far into that. And then the final step here is that we need to be able to learn. So this might be a sort of reinforcement learning type process where we're observing whether the actions that we took produced the outcomes we expected, or this might just be a development process where we're doing some sort of iteration on how we structured this problem to be able to produce the outcomes that we want to. So we've got techniques like RAG and few-shot learning that are all kind of mechanisms of learning in various ways. And so what I want to focus on here is primarily on this right side of this cycle, the watching and the triggering. Because I think these are the parts that technically are the most different than doing something like a support bot. And they're different because of this important distinction that I mentioned previously, which is they're not really like a call response type interface. We've got a lot of applications that are in this sort of, I'll call it like a function call structure, where you have a question that's asked, the model goes and thinks, and then it gives you an answer back. And then you're done. That transaction is complete, and you're not doing anything until you get another question. What I'm going to argue is that we need something more like this right-hand side. We need more of a streaming style application to be able to build these interactive, always-on applications. They need to be able to watch what's happening in the world as a stream. Some things we won't care about, right? There's a large number of events that are going to happen in the world that aren't relevant. We may not know that, though, until we've ingested them and done some analysis. And so this is, I think, the model that we need to use when we're building these types of applications. And building in this style requires different approaches in a lot of ways than building in this function calls world. The biggest difference is in how we handle data. So in a traditional application, you have a bunch of data, you stick it in a database, maybe you're modifying it, whatnot, and you bring queries and you get answers back. This is the sort of traditional model of how you would structure an application. It's optimized for being able to do arbitrary queries as effectively as possible. And it's done that way because that's kind of how we originally built these systems. We've got a bunch of data. We're going to answer analytic queries about it. And what I want to look at is how we can kind of change that structure to go from being what I'm calling lazy computation to eager computation. The big difference here is that we start in the lazy world with the data, whereas in the eager world, we start with the query. Up front, we define what is the operation that we want to do, and then we pass the data through that. What this means is that we can process each change much more cheaply because we already know what we're going to do with it. We can optimize the processing for the specific answer that we need to produce. And that allows us to generate these answers in real time effectively. This is the goal here, is that we want to be able to react immediately when things are changing. And so how do we go about doing that? At a very high level, kind of the general process here is that we take the operation that we want to do, we break it down into a single kind of thing that we're going to do each time some data arrives. In this case, we're going to compute an average, right? So we have a 6 come in, and then we compute a sum and a count, and we divide them and we get 6. When we get another value, we've got an 8 here. We're going to like increment the sum, increment the count. We know they relate to 7, and we can just do this indefinitely, right? The point here is that we can then take this state that we've computed and snapshot it. This is the only thing we need to store. We don't need to keep a hold of all this data. We can throw the data away. We're done. This means that we have a very different data utilization paradigm, and it means that we have very different latency results. This, however, is not what most people are familiar with building. This is a kind of a weird way of thinking about a problem, and the implementation is somewhat tricky. And that That's why we built Kaskada. So there's a couple of things that are difficult here. I'll probably just skip through this. Kaskada is a tool that makes it easy to build this type of computation. It gives you a sort of unified way to build queries, so you can build that yellow part really easily, and then multiple different ways of passing data through it. In this example, what we're looking at is we've got some CSV data. We're gonna build a data source, and we're gonna just count. We're gonna say how many rows have we got. And what you can see here in the bottom is that we're showing how that count changes as data arrives. You can see it's per user as well. So the count is 1, 2, 3, and then 1 because we got a new user. And so what this has done is it's gone and it's computed that kind of operational graph, and it's driving the data through, and it's done it all in batch. We can also do this in real time though. In this example, we've created a slightly different data type. It's got the same schema and whatnot. We're gonna asynchronously add 6 rows of data and then asynchronously consume that data as it comes out. So what this is showing is that we've been able to take the exact same definition, right? This is still just count the events. We didn't make any change to our code. And we transitioned from doing a batch analysis over all of the events that have ever happened to doing this in real time as it arrives and producing these results in microseconds. That wasn't a very interesting computation to count. No one You'd be surprised how many ML features are just counts. But obviously you can do lots more interesting things. You can filter, you can combine different things to create like dictionaries and records and whatnot. You can aggregate across different windows, sliding windows, rolling windows, whatever you want to do there. You can change how they're grouped. You can operate across groups. Basically all of the things that you would want to have done in that database world that we're all kind of familiar with, there's an equivalent implementation that you can do incrementally. And we give you a really simple kind of pandas inflected syntax for writing that out. The goal here is to have a library that is as easy to use as just like a pandas data frame, but lets you handle data incrementally without having to learn a whole bunch of new concepts. We do this, I'm not gonna go into too much detail here, but we do this because we've kind of started from a different foundation. SQL, pandas, a lot of these things are built on the idea of kind of tables. We've started with this idea of what we call a timeline, which is like a table with a time axis. So if you start with a data set full of a bunch of like information about what people purchased at various points in time, and then you compute a sum of that, those sums still have that time axis. What this means is that everything you do has time, and it means that we can always kind of play this forward one event at a time. And so we have like a slightly different abstraction foundation that we build on to allow you to do this unified computation across both batch and streaming. It's fast. I don't know if you guys are familiar with DuckDB. It's a really great analytic database for like computing locally. Their claim to fame is that they can like compute quickly enough that you probably don't need a big data database. We did a bunch of benchmarks against them. For most of these, we're kind of equivalent computational cost. This one right here, where we're like substantially faster than them, is where we're doing this historical analysis like we're looking at in the first example. This is really hard to do in SQL for various reasons I won't get into. And so to kind of summarize where we are, what Kaskada provides, we'll look at an example of how we can use it in a minute. Our goal here is to make it so it's really easy to get live data so that you can handle events as they happen and build these reactive applications that you're actively watching and triggering. We have this data model that makes it really easy to reason about. We have this syntax that's hopefully easy to get started with and doesn't require a bunch of complex stream processing background knowledge. And its package is just like a Python library. You just install it and you're ready to go. I think oftentimes when people hear about streaming, they think, oh, we're talking about Kafka, we're talking about big data, we're talking about all of these like complex systems. It's really just a different way of structuring your process. It doesn't need to be complex. And so what we've tried to do with Kaskada is make it easy and accessible. So, example, what we looked at here was kind of like, what is the structure of the problem we're talking about? How do we build these sort of interactive agents? We looked a little bit at Kaskada, a tool built to make this type of analysis easier. And I want to walk through this example app that we built to kind of like make this a little bit more concrete and show you what you can do with this. We call this thing Beat GPT. It's a Slack bot. It actually implements one of those examples that I talked about. It watches everything happening in Slack. We've trained it to understand what everyone in the Slack organization cares about. And when there's a conversation going on that it thinks somebody is interested in, it will notify them and say, hey, there's a conversation. So it's sort of like a smarter notification thing. So as an example, Preeti, product manager on my team, she left this message, hey, we're launching a new marketing campaign. Let me know if you have any suggestions. BeepGPT has learned that I tend to engage with these kinds of conversations, and it sent me this notification that says, hey, there's a conversation going on. You should pay attention. The way that we've done this is by using fine-tuning. So the first step in this process was we downloaded all the Slack history of our organization, and we used Kaskada to build a bunch of historical prompts. So these prompts are basically reconstructing what we would have asked the model at the time the conversation was happening, and then we've provided it with the correct answer based on the historical analysis. So this gives us a big data set of fine-tuning examples that we can just send to OpenAI. It's very fast, or it's not that fast. It takes about 12 hours, but it's very easy. We got our custom fine-tuned LLM, and then the second stage of this process is that we consume events from Slack in real time. So Slack has a WebSockets interface where you can get every event that happens in your workspace. We consume those with Kaskada. We build these prompts in real time in the exact same way that we built them during the training example. And then we send them to the LLM, and the LLM says, hey, you need to tell these people about what's going on right now. So let's kind of dive into that a little bit more. This is in the training stage. So one of the things about Slack, one of the reasons that you want to use something like Kaskada rather than just setting up like a Lambda trigger, is that each event that Slack sends you is just one message. That is not useful if you're trying to figure out whether a conversation is interesting. You need more context than that. And so what we're doing here is that we're aggregating across multiple events to create the state of the conversation at a particular point in time. That is the prompt. That is what we're going to give to the model in the future and say, who cares about this? And in this example, we're going to give it the answer, which is this person who responded next, Ben. We'll build a whole bunch of these. We'll send it to the model. This is the simplified version. If you're really interested in the details, we can get into it more. And this is what this looks like in code. We've got some messages. We pull out some fields we care about. The collect operation builds a list of like up to 20 consecutive messages. We do some formatting here. This is what OpenAI likes to see its data look like. So we're adding some delimiters and things like that. And then we build an example. So we say the prompt is the conversation formatted. The completion is the set of users that gonna engage with that conversation, formatted. We're not showing that. And then those we just execute based on the historical data and send off to OpenAI and wait for 12 hours until we get to the top of the queue and we get a model. Step 2, we want to use this in real time. So this looks fairly similar. We're still building up this conversation across multiple events because we need to be able to aggregate to get a fully fledged kind of understanding of what's happening. We send it to our fine-tuned model. This time the model tells us what it thinks the answer is. In reality, this is a kind of set of log probabilities over multiple potential users, and we'll use that as a threshold. But this is the simplified version. And here's what this looks like in code. Most of this code does not have to do with Kaskada specifically. We are adding a Slack handler, defining what to do with the message when we receive it, acknowledging the message, pulling out some of the data that we want to use out of it. And then this is the important part, is we just add it to the data set. We're doing this dynamically in the Python process every time a new message arrives. And then on the other side, this produces a new row and output every time we add a message. This is a new state of the conversation. This is happening asynchronously. We'll send that to OpenAI. We'll get some information back from them. We'll call this interested users on the response. And anyone who is interested, we'll send them a notification. The entire implementation of this is about 150 lines of code on the real-time side, and there's a notebook that we use to train, which is 200 some lines of code. So a minimal implementation of this is very easy. There's no infrastructure involved. You just run it in a notebook or on your computer. Obviously, we're using OpenAI for the actual training process and the hosting, so I guess there's some infrastructure, but you don't have to manage it. So just to kind of circle back, these are the kind of examples that I've heard about so far that are doing this type of real-time, proactive, watching what's happening in the world, building up an action that it believes is going to accomplish some goal that you care about, and and then acting on that. But I think there are more. I think this is probably, like we talked to Patrick a little bit about agents being the future. I think these are the use cases of the future that are all going to be based on this sort of real-time paradigm. So I'm very interested in understanding, if you guys are working on problems like this, please come talk with us about it. Also, if you're interested in using Kaskada, it's an open source project, Apache 2 licensed. This is the URL up there. This is our Slack. We would love to talk with you about what you're working on, what you're thinking about working on, whether Kaskada is a good match. And even if it's not, we're always interested in understanding what's happening in the market just so that we can make sure that we're evolving the product in the right direction. This is the example code for the Beep GPT. We've got a couple of different iterations. What I showed you was like the very simplest, easiest to put on a slide version of that. We've been iterating on that a lot. So we've got a couple of different versions of that. We've got a version that uses a vector database. We've got a version that uses Hugging Face models. We've got a whole bunch of different versions of what we saw that you could take a look at and see kind of like what the options are and kind of where Kaskada might fit into that. And so, yeah, I would love to talk with anybody about that. And that's my slides.
Awesome, awesome. Thank you, Ryan. Do we have any questions? Well, first, give him a hand. That was awesome. Deep dive. I love when we're getting into code. So we've got to raise your hand if you are a coder, if you touch code in AI, or you just touch code in general, and that's something that you're interested in. I hope some people. Oh, okay, yeah, we got a good percentage here, and so here we've got a broad cross section, and we like to dive deep and not just gloss over things. So hopefully everybody gets a bit of an education, find some inspiration and direction they can go. I'll pass the mic if anybody has any questions.
Hey, Ryan.
Hey.
Awesome. Awesome. So the first use case that springs to mind with just this one that you just showed here, which is pretty common, is actually monitoring across multiple different conversations, right? So, there's actually been SaaS services built, so that you could have connectors for all your things. So say you're an enterprise and you're grabbing this. My question is, do you have to train an entirely new model, to get other conversations from other, messaging type systems, say?
Yeah, so I think one of the shortcomings of what I just showed you right now is that the model is you've baked everything into the model. I think Patrick mentioned this, that one of the nice things about RAG is that you can kind of put a bunch of data in a database, and then whatever's in the database is what the model has access to. So I think that fine-tuning is nice for kind of solving like intuitive problems, whereas I think RAG is really good for solving more memorization type problems. And so there would be a need to do some fine-tuning periodically to recognize different contexts, different users coming and going. But I think that there are ways around that. So one of the things that we worked on, one of the kind of follow-on examples that we looked at was, instead of having a model infer what's interesting to each person, we just have the people tell us what's interesting to them. Basically say, like, I would like to know anytime this or that is happening. And now we have like a set of things that we can look for, basically. And I think that is a different structure to the problem that is probably better for this situation where you have kind of dynamic people coming and going, or wanting to use it across different like channels of data sources, yeah. But I think, in terms of just being able to handle multiple channels, this is one of the things that we think Kaskada is really useful for, is being able to take 5 or 10 different data sources and just kind of like combine them all down into like one unified view of what's happening for each user or for each chat room or whatever. I showed a simple example of just like one data source, but you're not limited to that. So, yeah.
Hi, Mike. My name is Puneet. Thank you. It was a great presentation.
Hey, thank you.
Especially the example. So I'm just digging a little bit deeper into the fine-tuning. Now, so my larger question is, are you fine-tuning at the application level? That means whatever learning you get from one customer are sort of applicable to all the customers and vice versa? Or you can further fine-tune in different slices? For example, you can literally go down and fine-tune for an individual Slack user, for an organization, or for different use cases. For example, Like, are you looking to categorize, looking to find something interesting? And then all those could be different fine-tuned models. And if you've tried a variety of these, would love to learn from that experience. Thank you.
Yeah, so I think what we showed right here was basically cross-organization fine-tuning on every user, on all the messages, just like throw all the data at it. We did this first because it was the easiest to do. It was just a simple solution to the problem. Let the model go figure out and sort through the details. I think that we've done some work using like Hugging Face models to train like Llama 2 to do roughly the same thing. And I think that those might be more appropriate for doing a kind of a user level type fine tuning, just because you have a lot more flexibility when you're dealing with some of the open models. OpenAI is okay, but it gets a little costly. Actually, I may have. Oh yeah, I have this slide in terms of like what this costs. So, we often get asked like, isn't this expensive, all this fine tuning? People assume that fine tuning is really expensive. On the corpus that we were training on, it started with about 20,000 messages, and then we did some kind of data quality enhancement that brought it down to about 2,500 training examples, and that cost, I don't know, $3 to train. So we did a lot of training cycles. The entire thing ended up costing a couple $100. But, if you're building a startup, these are not important costs. This is probably more important. We're talking about like a quarter penny per message. So, if you're dealing with a large, high volume data source, it might get spending. But I think this is just the cost of LLMs, really. Like this is what it costs. So, yeah. Yeah, well, in the open models, I think, one of the things that we discovered, we trained a bunch of different models. I don't think I have. No, this is not related. So we tried a bunch of the different OpenAI models to kind of compare performance. And what we found is that we started with Ada, and the results were trash. It was useless. We jumped up to DaVinci. At the time, the 3.5 wasn't available. And DaVinci was great. What was surprising, though, is when we tried that again with Curie, the performance was actually better, and the cost was substantially less. And I think this is because the sort of complexity of the problem that we were using was better tuned to that size model. And so I think what this suggests is that there's probably good applications of some of the open models, that they may not be 70 billion. You might be working with a smaller model, but if your problem is not as big as you need to have ChatGPT 4 working on, you may actually get better results using a smaller model that you can run on your CPU or something like that. So, yeah.
Okay, thank you, Ryan, and hopefully you'll stick around, and people
around.
can approach you and seem like an approachable guy. So thank you very much.